Okay, so it's my pleasure to introduce Steve Sun, currently an associate professor of civil engineering and engineering mechanics at Columbia, where he's been since 2014. Steve's research interests run the gamut from computational geomechanics to computational poromechanics to multiscale modeling of fracture, damage, and plasticity. Steve has, I believe, won just about every award our community has to offer to young investigators, including Young Investigator Awards from the AFOSR and ARO, the NSF Career Award, the Leonardo da Vinci Award, and the Zienkiewicz Prize. This afternoon, he's going to tell us about some of his recent work utilizing graph theory and multiscale mechanics. So Steve, it's all yours.
Thank you, John, for the introduction. So let me start the presentation right now. So, okay. So thank you very much, and I want to thank again the USACM for inviting me to give this virtual seminar. It's a great honor. So I want to start by showing us the beautiful campus of Columbia University. As you can see, yeah, New York is a very interesting and nice place. So today we will talk about something that related to geography, that I actually have some roots on the geography, and that is graph theory. And how do we apply graph theory to mechanics problem in the new framework that involves machine learning. Before I get to the details, I would like to first acknowledge my students that actually do the work. As you can see the title, those are the major contributors of this talk. And notice that I did not include myself. So you can see who's doing the hard work and who's taking the credit here. But so Nick Vanus is actually the student that are working on the undirect weight graph, and Kun Wong is my former student that allow at Los Alamos. They're working on the direct graph. So in the first half of this talk, I will focus on the undirect weight graph, and then the second part I will focus on the direct graph and the applications. So the first question is that what is a graph? And what are the common types of graph that are used in mechanics? Okay, so many people attribute the starting of the graph theory in 1736, where Euler attempt to visit visiting the bridge that are actually listed in the map without revisiting any path. And he found out that in order to actually generate these tools, he need to define the node set and the edge sets and connect it together. So this is the beginning of the graph. And nowadays we see a lot of applications, both in machine learning and in classical mechanics problem. And graph, one of the most important usages is to indicate relationships. So in the Wikipedia, you can see that the citation network, we can actually see the connection between which papers, which article actually relate to each other. Social network is also another very common type of graph that actually have a huge impact on how we make predictions. Okay, so shown here is one of the example where we the graph can be used to predict the political choice of individuals using the Facebook data. It can be also to detect fake news, okay, and applying in a chemistry problem. In the chemistry problem, there are molecules and atoms, and then they form a hierarchical structure. And of course, in the most classical sense, we are all engineers, and many of us are structural and civil engineer. We can also consider solving a trust system as solving a graph problem. Okay, so basically, in summary, graph is just nodes and edge that are actually combined together to form a network. Okay, so in this talk, I will talk about two types of graph that are actually have applications in mechanics. We will talk about weight graph. And weight graph is actually by definition is a graph that contains nodes and contain edge, but either the nodes or edge can have some weight on it, and that weight can be anything about the attribute of the structure. For example, in the pole mechanics, we often convert a void space into a network, and that network actually we use a weight to indicate the length between the two pole center, and that would actually constitute an average graph. And we can use the average graph to determine the tortuosity and conductivity of the void space. In solid mechanics, in polycrystal problem, which we're going to focus in the first part of the talk, the implication is that we can actually generate representations of the structure by analyzing how does the grain with different attributes connect together. So in here, we have a polycrystal. In each polycrystal, we have multiple grain. In each grain can form a nodes, and the nodes can also have property. For example, the graph, each grain can have different size, have different Euler angle orientations, can have different Young's modulus, and so does the edge. The edge can indicate whether the material is broken, intact, or actually what is the normal force that are applied to the material. So, and also another common way to actually use the weight graph is actually to store solutions. Let's say this is actually not our work, but from Christian. So what you see here is that is the linear elasticity solutions. We can use a deformation map to link different solutions together, and as a result, we have a set of solutions that are linked by the relationship among different solutions. And also one classical way to represent the conductivity of the force is a force train, which is also a weight graph. And in this case, the force train basically will have the normal force as the weight. So what you see here is a data structure that are actually in the non-Euclidean space. For example, in a graph, we cannot take a divergence or gradient. Basically, it doesn't make sense. But each entity can have its own value. So the challenge here is that how do we find the right mathematical machinery to operate those graphs or to using it to aim the mechanical predictions. Another type of graph that I will talk about is the one that with hierarchical relationships. For example, the family tree, literally. And actually this work can, the use of direct graph can go back to at least in 2018, in 2008, where the Ortiz Caltech group using the direct graph to model to actually remeshing tetrahedral's domain. So basically the idea is that we can form a body, and body can be composed of multiple volume, and volume would naturally have surface have edge has point. And then and as a result, when we try to remesh, we can think about it as generate a new branch into the tree that are actually store the hierarchical information. So we separate from the geometry problem to the topological problem by using it this way. We can actually modify the tree to get a new mesh. Another thing that we are actually also working on is actually the Lloss graph. Lloss graph has been recently have a lot of tractions in Google that actually represent different entity. But here, the goal we have here is to represent the constitutive law as a Lloss graph. A lot of constitutive law we can see here can be reconstituted as a Lloss graph that has used an input, for example, a strain history to output a stress, or relative displacement output attractions. The internal variable or the mechanics of the revolutions of the historical variable is related to how different physical quality are actually connected to each other. So another type of the direct graph that we have is a decision tree. So another application that I will talk about today is to design experiment. When we design experiment, we have a lot of different options to choose an experiment. For example, in a triaxial test, we can control how many confining pressure we have, what is the loading path, should we do unloading, if we do, what kind of combination do we want. So if we consider all the possibility together, it constitutes a decision tree. And each experiment is a walk in this tree. And so the goal of designing the experiment is how do we actually, given a finite amount of resource, find out the finite number of the tree that can, find out the finite number of the walk or the tree that can yield the best results for calibrations or for attack the model. Another usage of the direct tree is store time data. So unlike the spatial data, time is a one-way street. So the future is affected by the past, but the past will not affect the future. So here is another example, again, from Michigan to show that we can represent the relationship of different solution and different time using a direct graph. In this case, that would be just without any branch, that would be just different time step going from the earlier time to the later time. Okay, so this is the type of graph that we're going to talk about. And I would only highlight a few applications, one for weight graph and then one for direct graph. Okay, so the first part of the talk is on the applications on the weight graph. This is actually mainly done by my student, Nick Venus. So we actually confront a problem when we have a recent project on the modeling polycrystal or granular material. Okay, so shown here is two RVE, two pair of RVE. One is crystal, another is granular material. So we have the following problem. If the A and B microstructure have exactly the identical void ratio, have the same average orientations, have the same dislocation density, have the same grain size distributions. However, if the microstructure are different, we would expecting that the constitutive response are different. However, in this case, how do we write a material model if all the measurement we have are identical? Another thing is also very common in soil mechanics or in geomechanics. We have the material with the same void ratio and same confinement pressure. But as you can see, the microstructure difference would lead to a very different response. Here, you can see that because we have a very structured order of the particle, the relationship would be relatively isotropic, where this one will have a tendency to shear in a different directions, would have a different amount of shear response. Okay, so if they are actually statistically or volume averaging, or they're identical in the volume averaging sense, how do we describe one from the other? Okay, so this is actually one application where the graph will work, because inherently you can see that in the different material, even though the average property are the same, the graph, connectivity graph are already different. So the goal is to see how can we use the graph without the burden of entering the entire graph as the input to write the constitutive law. If we look back into the development of the plasticity or elasticity, we can actually consider some of the progress of different constitutive model are related to introducing new descriptor. So we can see from J2 to Juker project, we introduced the mean pressure as the functions to modify the U functions. For critical state soil mechanics in geomechanics people that are important for geomechanics, we introduced the dependent of the void ratio and over consolidated ratios in the hardening rules and the use. And in the recent work, we introduced the fiber tensor to actually introduce the right evolving anisotropy. What we can think about this history, that one of the major roles that are playing is the introductions of new descriptor that actually can help us to define the material and yet have something that are measurable. Okay, we can write a constitutive law by increasing the parameter or the number of internal variable, but oftentimes the real progress comes from the fact that we can identify something that we can measure and hence constitute relationships or actually generate a hypothesis on the relationship to make predictions. So from the mathematical point of view, this is equivalent to generating a direct multigraph to one exact direct graph. Okay, so So go back to the previous questions. How do we generate the descriptor is one of the tasks that we are facing. And what we are doing is the following. Okay, so I just want to show some of the examples that we're currently trying. Is that we would generate, in order to understand how does the topology of the grain arrangement or the grain property affecting the material, we would use a machine learning tools called graph convolutional neural network. And what we're actually doing is that we will run a lot of FFT simulations for different microstructure that actually have a corresponding graph. And we try to process the graph with unsupervised learning to generate a low dimensional descriptor. And using this as an input to make, in addition to the string measure, to predict kinematic measurement or energy. So mathematically, we can define it as the, for example, the Helmholtz energy or the elastic store energy of the material depends on the deformation, but also the initial polycrystal graph that define the conductivity. So you can see in that, unlike the common circuit supervised learning, where each RVE have its own supervised machine learning, what we're trying to do here is that for all the same family of polycrystal, we can generate one constitutive model that can deal with different microstructure. Each time we have a new microstructure, we can generate a new energy function that are different and distinguish the RVE from RVE 1 to 2 that are otherwise unable to distinguish. You can see here, this is the elastic energy functional that are actually changed according to C11 and C22. Without the graph, the two behavior would look identical. These two would be completely indistinguishable. But with the graph as an input, we can see which one is which, and we can see what is the topological change influence the elastic predictions. Okay, so our focus is on anisotropic material because inherently it's more interesting. It's also harder in some sense. And what we're actually trying to do here is that we will generate RVE with, we will generate 150 different RVE. Each RVE will suggest to 200 different combinations of the string, and then we constitute the data. In the later work, we will also working on generating the plasticity response, but here, I just want to show the work on the elasticity. Now, if we have a graph, we can have a lot of nodes and we can have a lot of edge, and that also amount into a very big input compared to the classical circuit model, where we often use only a few scalar or tensor as the internal variable. So the idea is that we need to find a way to represent the graph without actually inputting the graph as the input. So this has been done in a lot of classification problem, and one of the way to do it is the following. We would actually store the connectivity of the graph and feature in a different feature vector, and later on we will be using it for the convolutional neural network. So this is a very tutorial type of example, which is actually not used in practice, but you can actually see how we make the computations. The input for the convolutional neural network is a symmetric normalized graph Laplacian and the feature matrix. And what we actually need to compute is actually the degree matrix, which indicate for given locations how many neighbor does that graph has. So here, graph 1 have exactly 1 neighbor, graph 2 have 2 neighbor, and graph 3 have 3 neighbor, etc., etc. 1, 2, 3. And then we actually, and then we have defined another adjacency matrix, which indicate which neighbor, which graph is which graph's neighbor. If they're a neighbor relationship in the off diagonal term, you put a 1 there, and then we get the graph Laplacian. Okay, so but notice that in theory you can use the graph Laplacian, but then in some sense, in some case, you would want to get the symmetric normalizing one just to get a better eigenvalue spectrum. Okay, so with this, then we can actually generate a supervised learning example. So in here, what we actually do is something called semi-supervised learning. Also at Sandia, there are some work that are using the convolutional neural network directly using the image to obtain the feature vector. The here major difference is that we start with the graph, And if you look at it, so in the graph here, in order to represent this structure, I only need a 5 by 5 matrix, okay, and I only need a feature vector that are 5 by whatever number of feature I want to store. So the dimension of the input is actually much smaller, way before we do the convolutional neural network to further reduce the dimensions. But if we try to use a voxel image, we may start with something in much higher dimensions and then generate the feature vector that are equally small. So what actually happened is that we were using these two as an input, and then it passed through the graph convolutional layer to generate a low dimensional feature vector. And that feature vector would be used as one of the input in the supervised learning branch to actually change the stored elastic energy. So this is called semi-supervised learning because this part is basically a dimensional reduction task that are conducted in an unsupervised manner. And this part in here, from here to here, is just a classical supervised learning. I have a low dimensional representations of the microstructure that are used as an additional input to help me change the energy functional so that for a given string, I would have a stress measure. So the design is the following. So this part is an encoder. So if you're actually familiar with the machine learning literature, the encoder is one part of the autoencoder where we have an encoder and decoder. In the autoencoder, you input a graph, and what you want to do is to reduce the dimensions to the latent space. And then we also want to see whether the decoder can generate the original image. If I can reduce the dimension into a small space and yet output the same or something that are very close to the original graph, then I obtain the low dimensional representations. Okay, so in graph, it also gives you different machinery than the classical Euclidean space for you to compact or reduce the dimensions. So I will show some examples. So, and this is actually not our work, but we mainly read the literature and then use the available source code to put it together. So if we start with a graph, we can actually have a convolutional neural network that capture the feature. And then what actually happened is that we can also compress the data by doing a coarse graining for the graph. Unlike the Euclidean space, what we actually can do is that we can do something called pooling. And here is one example. So initially, the graph has a lot of nodes and edges together. But if we can find out the macroscopic structure, we can group multiple nodes into a super nodes. So 5, you can see that 4 nodes are grouped into 1 node. These 2 are grouped into 1 node. And then after the pooling, we will get a much smaller structure that will present the larger structure. And we can repeat that process until we have a very small data structure. And notice that if I know the mapping from here to here, from here to here, I did not lose any information. I just need to keep track of the mapping that help me map the small data to the original data. So ultimately what we actually do, and then after that, we generate a classifications to actually group different type of feature together. And then that would give us a low dimensional structure. Okay, so this is actually how we actually compress the data. In the supervising branch, I think that a lot of us are very familiar with it. We give the input and output as the training data, and we actually change the way to actually adjust the behavior. But what we actually found out is that if we actually use the string as the input and then output the stress, a lot of time the stress lost some desired property. And also the derivative of the stress is often oscillating and and the energy functional could be non-convex. So this is one of the problems that we have been working on for a while. And we seem to find some promising lead here is that when we actually when we actually want to generate a constitutive law, instead of outputting the stress, I would output only the energy. However, I would also use the first derivative of the energy, in this case, the stress measure as an additional input for the loose functions to help me adjust the voice. And then I can also use the second derivative, which is actually the stiffness components to help me actually regularizing the data. So notice that in this incident, I would not need more data. I just take advantage of more data that I already have. For each time step, I collect the energy, the stress, and the stiffness tensor, and then I utilize all of them in the training. So we can see the comparison. So this is the classical L2 loss function. If we change the strain stress pair, this is a result we can get. Okay. So we can see that it actually generates a good learning rate, except that it's not as good as the H2. You see that this is 10 to 8 order, minus 8, and this is 10 to minus 6. But the Euler is not only better for the L2. If for the H2, the higher order loose function training, we actually found that even if you measure it in the L2 norm, even if you optimize it, even if you measure the performance using the L2 norm, the H2 norm minimization yield a better L2 norm for the material predictions. So this is actually quite encouraging. So we can get basically 2 order more accurate results by just changing a little bit of the training. And we can also see the response. You see, this is actually just a very simple energy functional as a test problem. We can see that in the H1, not only the energy functional look alike, but then the stress are actually matching much better than the L2 training. Okay. And for the L2, for the H2, you also see more desirable result, and that is the less oscillation of the coefficients of the second derivative of the energy functional, which is actually the tangential stiffness matrix. Now, this is actually on isotropic material as a test. But if we go back to the polycrystal data, we can also see the trend here. In general, so what we see here is the calibration, calibrate RVE and unseen RVE. We can see that in general, the bind testing is doing not as good as the calibration data, which is expected. But you can also see that by increasing different amount of the nodal informations on the feature vector, we can actually improve the prediction by moving the Euler bar from the right-hand side to the left-hand side. So in the M1 scheme, the ray graph are actually using only the crystal volume as the weight of the graph. So this is only a single vector that are put into the convolutional. And what we get is the blue curve, okay? And then what we actually see is that the bind testing and the training are actually very similar. When we actually introduce the Euler angle of the relative orientation of the grain, and those grains are actually anisotropic, we can see that the graph start to shift into the left-hand side, which indicate the reductions on the Euler. And what we actually also found out is that in general, to get the principal values of the stress measure correct is much easier than finding out the right directions. And this is something that we are still working on how to improve the directions. But no matter how we write, we found out that the directions are usually the harder part to predict. And we can also see that in principle, we can add a lot of secondary attributes that are more or less important for each grain to make a better predictions, but the benefits start to diminish. So that would give us a sense of what kind of a single grain parameter that are important for the polycrystal. We also did more tests that are actually compare the FFT simulations that are actually not used in the training and testing and validations on the performance for the elasticity part. And we also did additional tests. This is the a graph test in the sense that if I change the order of the nodes, if I change the name of the nodes, whether I get the same result. And you can see that the order of the grain doesn't matter. And then we also check the convexity. Now, one remark we have here is the difficulty on expressing the tensor term and what is the best way to actually write the objective functions that can get the most benefit of the tensor property. And what we actually find it helpful is the spectral decompositions. Now you have a tensor, we change the eigenvalues by actually try to match the eigenvalue as much as we can. But the principal directions can be represented in multiple different ways. So if you take out the principal directions, we have something in the SO3 group, the special orthogonal group. So how do we compare two rotations that are actually different? Should we do it component by component? So that one, I think we all know that it's not going to work. But what we actually found out is that how do we measure how do we measure the difference between two rotations actually matter or make a lot of difference on the predictions of the accuracy of the principal direction predictions. So shown here is two results for one single crystal plasticity for FCC. So you can see that if you do a component-based training, okay, we can get the eigenvalue really accurate, but then it cannot capture the sudden activation of a slip system, which lead to the spin of the principal directions. If we do it in the Lie algebra, it turns to do much better. Okay. Another extension we try to do is to generate the homogenizations of crystal properties. So this requires a very careful data search. Again, typically either we do it in experiment or doing it in RV simulations. The simulations and the tests are both expensive. So what we actually did here is that we will first find the free yielding point in the piping, and we are assuming that the sensitivity to the hydrostatic stress is actually not that much. So we can actually basically do anything we can actually assuming that the shape doesn't change according to the hydrostatic plane. And what we actually try to see is to visit every corner and see what happened. What is the shape of the U surface. And I'm surprised that we find something very close to Chaska yield function for the polycrystal structure, and we still want to know why. But this is actually the general result. So as you can see, this is anisotropic. So when we rotate the crystal orientation, we get a different yield stress. And what we actually trying to do right now is to connect how does the revolutions of the encoded feature vector affect the shape of the yield function for given orientations. So if it's success, then we can actually capture a family of the polycrystal structure and understand how does the change of the graph connectivity affect the yield functions. And from that, then we can actually also work on the hardening. So the second part of the talk, I think I'm a little bit slow, so I would actually go a little bit faster. As usual, typically I just lost a sense of time sometime when I give the talk, but here it is. Another type is a direct graph. Okay, so direct graph actually, as we mentioned before, will present some kind of hierarchical relationships. So when you write a constitutive law, your input can be considered the roots of the direct graph, and your output is the tree. So what happened in between is actually something that can be actually represented by a direct graph. One way to think about modeling is that when we write a model, we consider all the possibility to write something that lead to a direct multigraph. And when we say we write a model, sometimes is equivalent to making the decision to say that I believe this causal relationship is actually what driving the constitutive response. In here, what the machine is predict is the relations. How does the porosity, fibric tensor, and then the geometrical measure affect the Jackson-Sackbergson law? Okay, so this can be done by constitutive modeling as a game of connecting the roots to the tree. Okay, so when we write a constitutive law, we actually if we idealize it as a process to connect the input to the output, we can actually use the AI to actually help us find out what is the right connectivity that lead to the graph, that lead to the predictions. And we can actually connect them by using a neural network of mathematical expressions. And we have tried both. And then what we actually happen is that in each graph, we would actually generate a model. what we are actually doing is you use the reinforcement learning to help us continue improve the predictions of the model. So shown here is actually the AlphaGo. So at the top, you can see that at the beginning, the AlphaGo doesn't make very good predictions. As time goes by, it goes better and better. The reason is the following. In each time we end the game, is either win or lose. But what actually happened is that we can use the neural network to predict the earlier policy values that actually govern how does the AI play the chess. The same for the writing the constitutive model. If you think about it as a decision-making process, playing the AlphaGo and writing the constitutive model mathematically, they are equivalent to each other. We are making the decision to think about how does different quality are related to each other and what is the mathematical relationship among them so that I can connect it in the proper way. So here in the meta modeling game, I'm not making the piece move, but I'm trying to figure about what is the mapping to map from one nodes to the other. And we use the reinforcement learning to actually find out what is the relative benefit of connecting the different variable in one way or the other, and update the Q table by actually repeat, try, and error. So this is actually what happened. So we have all the physical measurement that we can measure, and that constitute the initial game. And actually all the possible way to connect it would become the direct multigraph. And the model, the job of the AI is to generate exactly one direct graph that actually make the best predictions. So the training, I won't talk too much about the details for the sake of time, but you can see real tests that are actually published before. So what the AI did is that it would actually assign initially a random values on making predictions on the Q value. It would move according to the best Q values. So whatever that the AI consider the best would have the maximum Q value walk. And then once you connect together, it would actually subject it to the environment, which is the benchmark testing data. And that depends on the L2 norm, it will generate an update on the Q values to tell us a more accurate picture about the relative benefit of one modeling technique to the other. So we can see here, so we have 75 episodes, which means that we write 75 different constitutive law, not us, but from the AI automatically generate. And each time it turns to generate a better response. Okay, and at the end of it, then we can see that just after 75, the traction separation law predict a pretty good results. And this is actually also something that we can see that initially the model is actually exploring different techniques to write a model. And eventually we cool down the temperature to yield a converged response. Okay, so but here we also extend this game not for modeling, but for design experiment. And we also introduce multiple pair. The goal is actually sort of inspiring from one of the PI meetings. So if we have an experimentaler, if the model is fixed, but we have one modeler trying to calibrate the model, but we have another modeler trying to make the model look as bad as possible, it will motivate them to generate a different type of data, design a different type of experiment. And then what actually happening is that we can introduce an AI environment so that the two experimentalists can compete against each other to see who win off. So so in this case, the decision is represented by a decision tree, and in each game rotations, the protagonists and the advisory agents are actually each generate a different design of the test, and that is run by RVE or physical experiment, and then we compare the results using it for calibrations. And the deep Q learning basically is identical. In each time step, the experimentalists generate one experimental design, running it in the RVE or physical experiment, and the advisor also do the same, and then they calibrate and then test the data. And once we did that, we backpopulate the Q value so that they can improve their art of designing the experiment. This can be done in a parallel fashion. So we can see here, we actually starting the game, and then each of them design the test and then run the test and then calibrate it. And we can see the result here for the Jupyter. So the data is the DEM. So they are equipped with the DEM solver to run an arbitrary DEM. This could be a triaxial compaction test, triaxial extension test. The goal of the first agent is to make the model calibrate as good as possible. The second agent is to make it look as worse in the worst possible way. And through the collaboration, each time they share the data with each other so that they can learn, they can learn from each other to make the game even better. At the end of it, we will reach the Nash equilibrium, and then there is no more point to run more tests, and then the game will automatically stop. So in the exploration way, they would try different combinations of the loading test. You can see that the agent trying some loading and unloading almost randomly. But at the end of the game, you can see that both agents start to recognize the weakness and the strength of the model. So in the Jupyter, it's actually quite expected, the results. We see the Jupyter do really well on the monotonic loading, but is not doing that well on the history that have a lot of unloading and a combination of kinematic or rotational hardening. And we can see the result here. Eventually, we can actually see the tendency. We can also compare a more complex model that do better in the DEM. This is actually the Mansali-Devalius model that have better hardening mechanism. You can see the performance that are actually different. So again, the defense is done by the first agent trying to find out what kind of data the model have a strength on. And the attack is actually focused on finding what is a weakness. And we also compare with our checksum separation law, and we can see different tendency here. So this one in the works, at the beginning, you can see that it successfully attacked the model, which means that this is actually reasonable because at the beginning, the first agent doesn't know what kind of data that could lead to a very robust result. But as the game progresses, both of them are actually closer and closer to reach the steady state. We can see that the final outcome is what matters. You can see in this case, the machine learning checksum separation law can generate very good predictions. And when they share the same result, in the worst case, this is already the worst case, the adversarial attack can generate. Whereas compared to this earlier case, we can see that the attack is more successful as indicated by the score. So
hey, Steve, sorry to interrupt. I think if you don't mind, if you can wrap it up, because we do have several people that have started to enter some questions into the talk.
Okay, so I will stop. So I will stop in a few, maybe in 2 more slides. So so this is actually the heat map of the decision tree. You can see that for the model one that are in charge of the calibrate, it starts to actually figure out, initially it just guess everywhere is good. Eventually it find out the type of data it needs to best calibrate a given model. And the same for the attack, it find out what is a weakness and just stay there. Okay, so, and again, this is not limited to machine learning constitutive law. It also works for any constitutive law that you would want to test. So we can, potentially this algorithm can tell you the weakness and the strength of a given model in the decision tree. So some future work, we are also working on, as we mentioned at the beginning, our root is in geomechanics. So we also want to see what kind of if the graph is evolved with time, how do we best representing it so that we can generate the latent space for the changing of the graph. And another thing is the causal discovery. This also a very popular topic both in philosophy and computer science. This is in collaboration with our colleagues from Johns Hopkins. How do we actually find out what is the causal relationship about variable? So I will just stop here. So, but what I want to summarize is that we generate an indirect ray graph and then the direct graph. These two categories of graph have its own unique applications, and I hope that I convince you that for some of the problem, it could be helpful for us as a new tools to solve some of the old problem in solid mechanics. So this is the relative, this is actually the reference that we have. And I want to conclude by first thanking the sponsor of my research and also my student that actually worked very hard to making it happen. And I want to thank all the audience for patiently listening to me for all the time. Thank you.
Thank you, Steve. So for those of you who have questions that have been waiting patiently, if you want to type them into the chat space now, you can. In the meantime, I'll start with those that have been posed from the beginning. So I'll just ask the staff if they could unmute Naveed Shervani Tabar, and I apologize, Naveed, in advance for probably mispronouncing your name there. But I'll just read Naveed's first question. He says, when coarsening your graphs, is there any physical coarsening objective for the coarsening of your graphs, or is it solely based on spectral scores of the graph?
Yeah, I think that this is one of the reasons we use the semi-supervised learning. If you actually look at the branch, ultimately it's subject to the same loss functions, so that it actually turned to generate the latent space that actually improve the predictions of the supervised learning branch. If we completely cut it off as a two-step process, we may actually generate some low-dimensional representations, but that representation may not directly benefit the predictions. So this is actually why we have to combine it together. Is generate some kind of bias so that we can generate the low-dimensional representations.
Thanks, Steve. Naveed, did you want to follow up with your additional questions?
Yeah, so thanks for the interesting talk, first of all. And so my second question was, you mentioned that normalizing graphs, that basically normalizing Laplacian of the graphs gives a better eigenvalue structure. I was wondering from what aspect basically you're saying that, what basically benefit does it have, would it have?
Yeah, I mean, for the example that I show, it may not be so obvious because everything is more or less the same, but we may have other case where you have a more extreme connectivity or so, for example, in social network, that could happen. So in our problem, we always have 1 to 4 neighborhood. Maybe it is not that important. But,
right. And Naveed, I see you had one last question perhaps that you wanted to ask.
Yeah, so my last question was, so I actually wanted to follow up with the first question. One quick note that,
sure.
Yeah, if we have time. So my main question, basically, when you group two nodes together, what's your criteria for, I didn't understand basically based on your answer, what's your criteria for grouping nodes when you do coarsening in each step?
When you try to group two nodes, yeah, I mean, this is done in the convolutional neural network. After getting the convolutional neural network, we try to do the pooling. I think that in the training of the neural network, what you want to try is to find out the low dimensional representation in the encoder, so that if you apply the decoder, you get back the original structure. That may be the only, that would be the only criteria.
Okay, so you don't implement some sort of physical constraints on how to group these, like based on your specific problem?
I haven't, but I can totally see why in some cases that could be beneficial. So for example, if physically there are things that are assembled together, or another thing that we consider is the following. If you have a single graph, the single graph inside the undirect graph, you can also form a direct graph to represent how many edges you have, what is the surface area, this kind of stuff. So in that sense, you have another hierarchical structure. We can think about how to customize this to leverage the structure. So to answer your question, I think that is actually possible. It depends on the problem and the type of material. For example, I can think maybe metal material or architect material, they may have some inherent leverage. If you think about how to represent the data better, that could be something that worth to think about. But right now we do not do anything. We just try to see whether whether we can actually generate a representation well.
Thank you very much. And lastly, what are the input and latent dimensions basically for your network? Latent space dimension and input.
You mean the input of the nodes?
No, like the whole graph. What's the dimensionality of the graph that you input the data, and what's the dimensionality of the latent space in your work?
So the unsupervised learning for other applications can go for very large graph. We haven't tried something really large, but we tried something ranging from maybe 50 grand to a couple thousand per particle. But I think that we can potentially try way more if we actually, because what we are doing basically the spectral methods. So ultimately, we can actually effectively try. I think in general, the size of our problem compared to the social network is much smaller. Or let's put it that way. Yes.
Thank you very much.
Yeah, thank you, Naveed. So the next question I'll read from Hojat. The staff can unmute him or her. It reads, in the real world, apart from the microstructure, the macroscopic response could be the same. How is that considered in your approach? In other words, for different microstructure, we might have the same macroscopic response.
So if you have the same microscopic response, I mean, I don't understand. Maybe I need to understand it. If you have the same different, so what we are trying to do is to find a handle so that we have a unique one-to-one mapping. But what actually could happen in the case where, you can certainly have different microstructures to have same response. But in that case, I was still thinking that we still need to figure out why they yield to the same response. So if we see that, I will actually certainly see how can we train two different graphs and come up with the same macroscopic response. So, yeah, I need to, yeah. So that would be my understanding.
So Hojat, I see that you have a question there that I skipped over as well. I didn't know if you wanted to ask that now.
Hi, thanks for the talk, Dr. Son. I had another question. How much would be the computational cost for a real-world problem if you were to run this code on that case?
So I was saying that one of the major motivations for us to switch from the Euclidean, from the classical convolutional neural network to the graph is the cost. You can see that if I have a voxel image, 1,000 by 1,000 by 1,000, and then it's a color map, I'm looking at 1 billion of voxel that I have to manipulate. I have to generate the feature vector. In the graph, I start with something much smaller. You see what I mean? In the graph, I have two sets. Okay, not one node set and one edge set, and have some weight. But then we can see that the dimension is already reduced before we do the convolutions.
Okay.
But to answer your questions, I think it depends on the computer. We have HPC, but we never do anything beyond the 2 nodes. So I think it's pretty accessible to most researchers.
Thank you, Hojat. So the next question we have is from Sadiq Kidwai. So if we can unmute Sadiq. So Sadiq is asking if you can shed some light on the uniqueness, stability, and convergence characteristics of these schemes.
Okay. This seems to be a difficult question to answer, but I think one of the reasons that we try to do the H1 training is actually to maintain the convexity, and through the convexity we can actually get some nice property about getting a unique and stable solutions. As for the general case, I think it depends on uniqueness and stability of what prediction. So I can say that for the elasticity response, I was saying that predicting a hyperelasticity model is mathematically an easier task because you know what you sign up to and you have the geometry that you can play with and to ensure. And the convexity basically can help you get the uniqueness and stability because you have the length scale. For the back box mapping is actually harder to tell. I was saying that if we just thinking from the string space to get the stress, we may certainly get the stress, but it's hard to check whether we get the good results. Another thing that could be tried is that if you generate, we can try whether you see the one-to-one mapping is that if we can do one supervised learning on using the string and get the stress, and then do another training from the stress to the string and see whether they yield similar behavior. That is more like an ad hoc approach. But my favorite is actually using the energy, because that simply give you more. And then for the implicit mathematical model, you really need the tangent to have some smoothness, and then the higher order training can actually give us the smoothness that we need to arrange the code. If you have a very good stress string response, but they are kind of bumpy, then the tangent would be very unstable. I don't know whether I answered that question well, but from the practical purpose, I think this is a necessary condition.
Sadiq, did you have a follow-up, or was that?
No, John. I'm satisfied for now. But certainly,
okay.
With any complex scheme and method, I think it'll be good to have some sort of confidence level, developing. And I guess WaiChing and Steve would write a paper in CMNAME very soon on these issues too.
Thanks, Sadiq. So maybe the last question, Suzanta Ghosh has a question. It reads, what are the criteria for the edges for the polycrystalline material? Is it only the interface area or their angle as well?
Oh, right now, I assign an edge whenever they're in contact. So the weight, there is no weight on the edge. But this is one of the interesting things about the edge, because imagine that when we propagate a grand boundary factor, for example, or something like that, we can certainly have a graph that are both node weight and edge weight, and the edge weight can represent some microstructure behavior. On top of that, I was thinking that acting the surface area, it seems to be a good no-brainer to start. But we can also include other aperture, other feature that could be potentially beneficial. For example, roughness, okay, or friction angle. So, but then right now we haven't tried anything on both the node edge range graph. But this is something we are very interested in doing in the future.
Thank you.
So thank you. And so maybe Shuzanta, did you have a follow-up, or is that okay?
No, that's a good one. Thank you.
So we just did have one last question. So Shashank Path Rutkar has a question. Shashank, would you like to go ahead? Let's see if I can unmute. Can one of the staff unmute Shashank?
Yeah.
Go ahead.
Can you hear me?
Yes, we can hear you.
Yeah. So on slide 13, you had a diagram or schematic of your framework. I just had a doubt regarding that. So once you obtained normalized graph Laplacian and feature matrix, and then you map it to feature vector, that is done through plain CNN, right?
No, it's done for the graph convolutional neural network, not the classical CNN.
Okay, and then again you incorporate deformation tensor with the output of first network to obtain energy functional. That is mapped through what network?
So right now what we did, the graph that you input is only the initial undeformed configurations graph that are actually coming from the undeformed configurations. It's not evolving right now. So what we try to do is we try to determine the relationship between the initial configuration. How does the initial configurations affect how the energy function will look like in the stress space, or sorry, in the string space? Okay, so you see what I mean? We are not yet able to doing it by actually capturing the revolutions of the graph yet, but that may be something that we are thinking about in the future. Those things that capture the revolution of the graph is called inductive graph, if I understand correctly, but I'm not quite there yet. So hopefully in the future we can try. But if you try to do it in time history, you have even more rich information. For example, what is the stress contour? Should I do a POD on the stress contour to generate some descriptor on the single grand level? So it opened another box of opportunity, but then we need to think about what is the best way to attack that problem. But this is actually definitely our next step.
Okay.
Thank you. Thank you. And thank you, Steve, again, for a great talk and your availability for the Q&A. I'm sorry we have to end this. I'm sure there are many more questions, and I would just encourage those of you that didn't get a chance to ask Steve a question today to reach out to him by email. I think you all know where to find him, and I'm sure he'll be happy to answer your questions. And as a reminder, we'll have another seminar next week. So we just encourage you to look out for that announcement and to register for the talk if it's a topic of interest. Thank you all very much for joining us today. We appreciate it. Thank you, Steve.
Thank you, John. Thank you. Appreciate it.